Our next application of equilibrium is titrations. These are widely used in different applications to figure out the concentration of different substances. And we'll see that by using equilibrium to analyze a titration, we'll get additional information about the different substances that we're titrating. So a titration is a method to determine the amount of a substance, known as the analyte, by adding a known quantity of another substance, the titrant. And our idea is that this reaction goes to completion. So we have an analyte down here, a titrant in this burette. We keep adding our titrant until we reach what's known as the equivalence point, sometimes the end point. In this case, for this phenolphthalein titration, it's this familiar faint pink color that we're aiming for. And the reason we want this is this will let us figure out what is in the analyte, what its concentration is. So we can use this to determine moles of H plus in, say, an acetic acid or vinegar sample, or the fatty acid chain length in a fat or oil. It's also used in environmental chemistry to figure out the amount of dissolved oxygen in water, and therefore to know if your water source is starting to become depleted of oxygen and therefore potentially no longer could sustain aquatic life. Many, many others. Really, really common application. How it works is this key fact down here. At the equivalence point, we have just enough titrant added to react completely with the analyte. And so therefore we can just use the stoichiometry of the balanced equation to determine the amounts at that particular point. We then detect the equivalence point with an indicator or by measuring pH or conductivity. Any measurement that we can do, we're going to identify the equivalence point from that key point. So in all these applications, we're figuring out how much X was in this beaker initially by adding some known concentration titrant to it. Here are the key terms for titration, just for reference. Analyte, that's usually what's in this flask. Titrant, what's in the burette. We're usually going to use a standard solution for one of the analyte or titrant. An indicator is often used to determine when you've hit the equivalence point by watching the indicator change colors. End point is when we end adding the titrant, and again, the most important thing is that equivalence point, when we've added just enough titrant to react completely with the analyte. We're going to look at several different types of acid-base titration, and again, the two ways we'll do this, say in lab, will be by looking at the color change of an indicator, looking for a nice faint pink of our phenolphthalein indicator, or a pH meter, just watching the pH and keeping track of that as we add titrant to our flask over and over. In each case, what's happening as we add titrant is that there's going to be a reaction between our analyte and our titrant, and that's going to go to products. What we need in terms of equilibrium is this to be a reaction that greatly favors products. So we need that forward equilibrium arrow with a one-way arrow there, so that K is very, very large, and this reaction, any titrant, immediately reacts with the added analyte so that we can quantify the analyte. Because we're in this case where K is much greater than 1, we're just going to be able to use the stoichiometry of this balanced equation to relate the moles of analyte to the moles of titrant. So just as a prelude to doing that equivalence point calculation, remember, you're responsible at this point for knowing molarity, the definition. Capital M is moles of our substance divided by liters of solution. And remember that you can write a molarity like 0.124 molar. That is equal to 0.124 moles per liter. But we can also use that as a conversion factor. So 0.124 moles is equal to 1 liter. And that way we can use it in a stoichiometry calculation in terms of, okay, we're going to put 0.124 moles maybe on top, 1 liter on the bottom, and convert to, say, moles or something like that. And that way we can stack our stoichiometry calculations just like when we do a grams to moles, maybe all the way back to grams type stoichiometry calculation. We might stack several of those steps together into one line. So let's use this as an example. For the titration at right, where you have 3.4 milliliters of 0.124 molar titrant that reacts with A, so how many moles of A are consumed in that process? Okay, so a reminder of how these work. When we're doing a stoichiometry calculation, we always want to start with a quantity. So a sort of quantity of the given substance. That quantity might be grams, it might be liters. Really, for our purposes, it's going to be grams or milliliters. Then in general, we always go to sort of moles of sort of our known or the given. And then we're going to go to moles of desired. In some problems, we can go all the way to the actual grams or milliliters or liters desired or something like that. But I think it's often convenient to stop at moles for a titration because that's often as far as we can get. Now, let's apply that here. So the quantity given to moles desired. So 3.4 milliliters, that's our quantity. So we can start there. 3.40 milliliters, and our substance is T. Then if you notice, our conversion factor is going to be 0.124 molar, so 0.124 moles is equal to 1 liter. Because of that, we need to get from milliliters back to liters, and we can do that right in our conversion factor here. It's 1 liter is equal to 1,000 milliliters, so we can stack that conversion factor first. That will get me to liters of my titrant. Then the next thing I want to do is get to moles. So to get to moles, I'm going to add on the mole to mole, not the mole to mole, the conversion factor here from the molarity. So 0.124 moles is equal to 1 liter. I have liters, so the thing I have already always goes on the bottom. So 1 liter, 0.124 moles. If I'm keeping track of that, I now have, not moles, liters has now canceled. Now I'm in moles of T. The nice thing about setting this up as a stoichiometry calculation is I can just keep going. I have moles of T. Now I can go from moles of given to moles of desired. So 1 mole of A is equal to, 2 moles of A is 1 mole of T using the coefficients from the balanced equation. So I'll do that, take the thing that I have, which is T. So I'll put 1 mole T on the bottom here, 2 moles of A on the top here. And that will give me the final conversion factor. Moles of T is gone, and I now have moles of A as my final answer here. My final answer, 8.432 times 10 to the minus 4 moles of A. If I look at my significant figures, I have 3 significant figures here, so I should round that back to 3 significant figures. If the answer, just 8.43. With that example out of the way, now let's go through an equivalence point calculation for a strong acid, strong base titration. The steps that we're going to follow to do one of these equivalence point calculations is 1, write the balanced equation. To get that balanced equation, I need to look at my analyte and my titrant and react them together. So in this case, HNO3 plus NaOH makes, I can do the products here. We can view it as sort of a double displacement or metathesis reaction. The H in HNO3 pairs up with the OH minus from NaOH, and some of the Na and NO3 pair up. That's the acid plus base make water plus salt idea. I'll write that as HOH as my liquid there, just to emphasize that this H came from the acid, the OH came from the base, plus NaNO3. So this is water plus salt. Often the products of an acid-base reaction, always when we have strong acid, strong base, that's always the products. Now, I need to balance it then, and the way I can balance an acid-base reaction is just by thinking about the acidic protons and the basic OH minus ions. So in this case, I have 1 acidic proton here, 1 basic OH minus there, and that 1-to-1 ratio exactly balances our equation. So there's no coefficients needed here. Just make sure the acidic protons match the basic OH minus groups. Next, we're going to use that given information to get moles of known. So one of these sides is going to be known. We're going to have enough information to get to moles. Then convert to moles of unknown. That's a mole-to-mole conversion where we need that balanced equation to do it. In this case, when we look at the given information, we have both milliliters and molarity for nitric acid, so that immediately tells us that we have enough information here to get to moles. So this is going to be our known side, and that then leaves the NaOH as the unknown side. And the equivalence point volume that we're trying to calculate is the volume of NaOH at the equivalence point. So that makes sense that the NaOH is sort of the unknown side of this titration. Then we start, as for any stoichiometry calculation, from a quantity of the known thing. So we'll go quantity of the known, or given. There's only one quantity given here too, so that's nice. The quantity given here is 50.00 milliliters of nitric acid. I'll write that as just HNO3. Then I can convert to liters, just as I did on the previous example. Now I'm in liters of liters of HNO3. Then from liters of NaOH3, I can do a conversion to get to moles. Remember, I always want to get to moles. In this case, I can get to moles using the molarity. So 0.0884 molar means 0.0884 moles is equal to 1 liter. So 1 liter is what I have on the top right now. I put that on the bottom. And I put 0.0884 moles on the top. So this first piece now actually tells me the moles of HNO3 present at the equivalence point. If I want to know the equivalence point volume, which is the volume of NaOH that I'm adding, I need to go from from HNO3 to NaOH. There I'm going to use a mole-to-mole conversion factor, which in this case is just 1:1, so times 1 NaOH for every 1 HNO3, just using that all of these coefficients happen to be 1 in this case. And now I have done step 2 here. I have gone to moles of unknown. That's let me calculate that the number of moles of NaOH at the equivalence point is 4.42 times 10 to the minus 3. Then the last step here is to use that equivalence point moles that we calculated and the rest of the given information to solve for what we need. In this case, I want the equivalence point volume. So given the fact that I know moles and I know molarity, I can say use the definition of molarity to get the volume, right? So I could just plug back in and say molarity is equal to moles over liters. When I do that, I can rearrange that equation by multiplying both sides by liters, and therefore get and divide both sides by molarity to get liters is equal to moles over molarity. And to say then I can do 4.42 times 10 to the minus 3 divided by my molarity. Now I'm thinking about NaOH, so I need to use the NaOH molarity, 0.098. And again, that molarity is moles per liter. So when I take moles divided by moles over liters, I will get a volume of liters of NaOH at the equivalence point, or that's how much NaOH I need to add to reach that equivalence point. I have 3 sig figs here, so I get 0.0451 liters, or I could convert that back to milliliters and get 45.1 milliliters of NaOH added. For this titration, that 45.1 milliliters of NaOH added, I expect to see that dramatic change in the solution and that change in, say, my phenolphthalein indicator from colorless to that nice light pink. Note that I do normally get more sig figs in a titration, 3 or often even 4 significant figures, because this is a very precise type of measurement that we can do with a high degree of accuracy and precision. Let's look at those 3 types of acid-based titrations. First, titrating a strong base with a strong acid. In this case, that would let us determine the molarity of a standard solution of NaOH. So we dissolve our base in the water, add a little bit of indicator, and start adding HCl from the burette here. So that's where our titrant is going to be. Now, as we start adding that, we are bringing in H+ ions from the HCl. Since HCl is a strong acid that dissociates fully, the pH starts to decrease. The actual reaction that's going on is the OH minus from the NaOH is neutralized by the H3O plus from the acid. This is a reaction that has a very, very large equilibrium constant, so it does instantly go to completion. Anytime I add H plus or H3O plus, it is going to immediately react with OH minus. This is what this looks like on a chart showing pH on the y-axis and milliliters of HCl added on the x-axis. So in this case, our balanced reaction is shown up above, and the picture of what's going on in the solution is shown on the right. Now at the left, we've got the starting point here with only base. Now as we start adding that HCl, we're going to start gradually approaching this equivalence point. So you can see on a graph of pH versus HCl, the equivalence point shown right here is this sharp decrease in pH. Before the equivalence point, the pH is gradually decreasing as HCl is added. Again, what's happening is that each of the H3O pluses that we add reacts with an OH minus and forms water. Again, we add another HCl in this little cartoon version. The next HCl that we add is actually enough to completely react with the OH minus. At the equivalence point, what happens? Well, here's what this looks like in our beaker here. The H3O plus that's added reacts with the OH minus, and now we just have a solution that contains the products here. So since we've used up all of the NaOH, we now just have a solution of water, and the only thing that's not water in the solution is NaCl. NaCl, though, is a Na plus. That's a cation from a strong base, right? Group 1 metal there. And Cl minus is the conjugate base of a strong base, or of a strong acid. So since Cl minus is the conjugate base of a strong acid, it's an ineffective base. Neither of these things affects the pH. Cl minus is an effective base, Na plus is an effective acid, and so on net, the product here is a neutral salt. Because it's a neutral salt, the pH is exactly equal to 7. So you can always tell the pH at the equivalence point by looking at the resulting salt that's formed from the acid-base titration. Now, after the equivalence point, we just start adding excess acid, and now we just have a solution that has excess H3O plus, and we get a very strong acidic solution after the equivalence point. Here's another example going the other way, starting with HCl, titrating it with NaOH. That's something you have done or will do in lab. In this case, we see the same idea. We start with a nice strong acid solution down here. The strong acid gets less and less concentrated. And then again, we still see the same sharp rise in pH at the equivalence point. We still have at the equivalence point a perfect pH of exactly 7.00 because the product here is NaCl, a neutral salt. Or again, in the net ionic equation, the product here is just pure water. So we just have a solution of pure water at the equivalence point. Afterwards, we end up with this excess strong base. You can keep track of the pH point by point in this titration. Notice here that we have a change at the equivalence point here is exactly 10 milliliters, and in just 0.4 milliliters on either side, the pH changes by a gigantic amount. It goes from 2.5 to 11.5, so about 9 pH units in, that's more than a few drops, but not much more. That's maybe 8 drops. This just gives us that information about the fact that we have only water, acidic or basic, at the equivalence point, again because of forming this neutral salt. Again, cation from a strong base, anion from a strong acid makes a neutral salt. Ineffective base for the anion, ineffective acid for the cation. For a strong acid, strong base titration, then we really only need to worry about the stoichiometry of the balanced reaction. 0.1 molar HCl here with only one acidic proton takes a certain amount of base to neutralize. If we have 0.1 molar H2SO4, which has 2 acidic protons, we can see that it takes exactly twice as much base to neutralize it. Now let's move on to thinking about the titration of a weak acid with a strong base. So in this example, let's look at butyric acid, which has a pK of 4.82. This is the yellowing, sort of off-smelling thing that is produced when butter goes rancid. So to check the quality of butter, we could make a solution containing the butter, isolate the butyric acid, and then titrate to determine the moles of butyric acid in that sample to figure out if it's above the threshold which makes the butter basically rancid. In this example, let's just consider taking a known concentration solution of butyric acid, so 100 milliliters of 0.1 molar butyric acid, and we're going to titrate it with 0.2 molar NaOH. So in this case now, we've got our starting point here. At the starting point here, we just have a weak acid in solution, but the curve does look quite different compared to the strong acid. We still have the equivalence point here, so at the equivalence point, we're still seeing, in this case, since we started with an acid, a sharp rise in pH. But the chemistry of this reaction is pretty different. So let's look at that in our sort of cartoon beaker over here, where each one of these represents basically 0.01 moles of the acid or base. Start out with a weak acid. Notice initially we see a pretty sharp rise in pH for this particular weak acid. That's because the first thing that happens here when we add NaOH is we add those OH minus ions. Each OH minus that we add reacts fully with the HA that we've added. That's always what we need to be the case in a titration. So OH reacts fully with HA. The products now, though, aren't just water, though. The product here is a little bit of A minus, the conjugate base of the weak acid HA. You'll notice that this type of solution, where I have a significant amount of HA and the significant amount of its conjugate base A minus, is a buffer solution. So as soon as we start adding base to our weak acid, we enter this buffer region where the pH is nice and flat over a pretty long stretch here from, in this case, maybe about 5 to 45 milliliters of NaOH added. In the buffer region, we again have a buffer, and so the pH in the buffer region could be calculated with the Henderson-Hasselbalch equation. The particularly important point that's useful for characterizing the weak acid is what's known as the half equivalence point. So this is exactly halfway to the equivalence point. It's the point we've shown here, where if I started with, say, 2 moles of HA in solution, if I ever add 1 mole of OH minus, I take my 2 HA and I take half of them and turn them into the conjugate base. At that point, I have, in this case, 1 mole or 0.01 moles of HA and that same amount of moles of the conjugate base. At that point, according to my Henderson-Hasselbalch equation, I'm at the point where pH is equal to pKa. Remember that for a buffer, we can always use that equation to get the pH. pH is equal to pKa plus log of the base over the conjugate acid. And so at that halfway point, we have the best buffering point. That's where this slope is the least steep. It's the flattest region of the curve here. And we have pH is equal to pKa. This lets us determine the pKa of our weak acid from this half equivalence point. So we find the equivalence point volume, in this case 50.00 milliliters. We cut that volume in half, go to the half equivalence point, and that lets us read out the pKa of the weak acid. Really important and useful way to measure the pKa and the Ka of our weak acid. As we keep going, we keep adding OH minus. Now we do reach that equivalence point. At the equivalence point, we add more OH minus, which reacts with the HA. If we look at what that solution looks like now, based on this key reaction, the thing that we have in solution is A minus, the conjugate base of HA. A minus, though, is not an ineffective base. Because HA is a weak acid, its conjugate base, A minus, is by definition a weak base. So since A minus is a weak base, at the equivalence point we have a weak base in solution and we have a slightly basic solution. If we look at our pH here, we're a little bit over a pH of 8 here at the equivalence point because we have that weak base in solution. So it's that concentration of A minus that's controlling the pH and making it pH greater than 7, again based on that weak base. Then if we keep adding OH minus, now there's nothing else interesting happening here. Now we just reach a part of the curve where we have excess OH. If I go the other way and start with a weak base and titrate with a strong acid, I start with a weak base in solution. Then I enter the buffer region. At the buffer region, it's the same idea. We still have pH is equal to pKa at the half equivalence point. We still have a nice buffer region. Even though we start with a base, it's not pH is equal to pKb or something like that. It's still the pKa. Then when I get to the equivalence point, because I'm titrating a weak base with a strong acid, the strong acid sort of wins out and makes the pH basic, or makes the pH acidic at the equivalence point. We can also see that based on HB. Since B is a weak base, its conjugate acid, Hb plus, is a weak acid. And so this leads to sort of an acidic salt at the equivalence point and a pH less than 7. It does sort of work, though, just to think about, like, the strong acid wins out over the weak base, and if it was the other way, a weak acid titrated with a strong base, the strong base would win out and force the pH greater than 7 at the equivalence point. That's another way to think about it. But other than that, same information, we can still use the equivalence point here to find the moles, cut it in half to find the half equivalence point. Really the same information, except now we have pH less than 7 because we have that weak acid in solution. Again, we still have that dramatic difference depending on exactly what the pKa of the acid or pKb of the base is. If the pKb is 4, that actually means the pKa is 10, so that's why this is the curve up here with the pH is equal to 10 at the half equivalence point. But same idea, just in reverse here. Okay, another conceptual point are acid-base indicators. So these change color to signal the end of a titration. The most common indicator would be some sort of weak acid or base that is very, very strongly colored. So even a very small amount of it gives you a very deep, easy to see color. Something like phenolphthalein, for example, the acidic form here is colorless. The basic form is pink. So once I make the solution basic, sufficiently basic, I have the transition from the colorless to the pink, and I see that dark pink. As I start getting sort of a medium amount of the pink, that's where that's where I can start to see the pH changing. Now, because of the way buffers work, what's happening here is this transition between the acidic form and the basic form happens at a pH equal to the pKa of the indicator. So that's what's shown here, is whatever we call it Kn or pK indicator, but this is really just pKa for the indicator. And we can see that we want to find an indicator with a pKa roughly equal to the pKa, where our equivalence point is going to be, so we can see the change. So phenolphthalein, which people use a lot for titrations, has a slightly basic pKa, or pKa of around, in this case, say 8.7. So we can see the color change in that region of 8 to 10, which is in the region where a strong acid, strong base titration is sharply increasing. For different titrations, though, we might want to use different indicators depending on what we expect the pH at the equivalence point to be. This shows that on a graph here. So for a strong acid, strong base, this is a great choice. Phenolphthalein works well for strong acid, strong base, the blue curve. It also works well for a weak acid, strong base titration because there our pH is a little bit greater than 7 at the equivalence point. So we're in that steep part of the curve for the weak acid titrated with the strong base. Methyl red, however, would work for the strong acid, strong base because we see such a sharp increase in pH. So it would go right through that sort of orange or red to yellow color change at the equivalence point, but it would be a terrible choice for acetic acid because it would start changing colors long before the equivalence point were reached. So these are sort of show the pH at different color ranges for different indicators. Again, you can just see that what you want to do is find one where the change occurs in that at the equivalence point. So here's a problem. What indicator would you use if you're titrating HNO2 with KOH? So in this case, we're titrating a weak acid with a strong base. We don't know the exact pH at the equivalence point, but we do know that the pH is going to be greater than 7 because the strong base sort of wins out. If we think about the products of this reaction, it's going to be HNO2 plus KOH goes to HOH plus KNO2. And so since that's the products, KNO2 is the salt that we form. K plus is an ineffective acid, doesn't affect the pH. NO2 minus is a weak base because HNO2 is a weak acid. So that makes this basic at the equivalence point. And so therefore, I'm going to want a pK indicator that's greater than 7. I don't know exactly where I'm going to be, but definitely that rules out these three out of hand where the pKa is less than 7. Now, bromothymol blue, maybe that would work, but if you look at where it's changing, it's going to probably change a little bit too early. So I would probably rule that one out as well, just because the pH range only goes to 7.6, and a lot of times the pH at the equivalence point would be closer to 8 or maybe even closer to 9, depending on what the weak acid is. So this one's probably going to change a little bit too early. That just leaves phenolphthalein and thymol blue as two reasonable choices. Since their color changes really start at around a pH of 8, that should be comfortably in that region where we're in the steep part of the curve and where we can start to see the equivalence point and not just the sort of the buffer region pH change. Here's one final example problem. Try this one out and then I'll show the solution. Okay, so we have sulfuric acid titrated with sodium hydroxide. The equivalence point is reached when we have 35.08 milliliters of NaOH. So the chemical reaction that's occurring is always the first thing we want to write out. In this case, H2SO4. Aqueous reacts with NaOH. Leave some extra room here. Aqueous goes to, the products are, you can view it as a double displacement reaction. OH reacts with H. So we're going to make water, liquid, plus the other product is the other two ions. Na pairs up with SO4. To fully react, though, we do need to go all the way to the end here. So I'm going to make Na2SO4. Just think about it as like a double displacement reaction. The two hydrogens have to be replaced here by two sodium plus 1 ions. Then to balance it, again, I need to make sure that the number of H's and the number of OH's is equal. So here I have 2 H's, but only 1 OH. So I'm going to need 2 NaOH's to balance that. Now I can use a normal sort of double displacement reaction approach of ping pong over to the other side. 2 Na ions, that's here, that's good. But if I look at S2O4, one of those, ping pong over to the other side. There's one SO4 on each side. 2 H's here, ping pong over to the other side. Well, here I have only one H, because remember, if we think about water as HOH, this hydrogen came here, so that I need one more water molecule to get all my coefficients right. Now I have 2 H plus ions and 2 OH minus ions. The OH minus ions came from here, and those do match. So that's the balanced reaction occurring here. Na2SO4 is a normal aqueous species here. Anything with a sodium ion in it is always aqueous, just floating around freely in solution. That's A then. Again, to get the sort of business part of the reaction, you can just see that there's one OH here, 2 acidic protons here. So to balance that out, I'm going to need the 2 in front of NaOH to make the H plus and the OH minus ions equal. We can see that here in the 2 moles or molecules of water that have to be produced as we strip 1 and then a second proton away from H2SO4. For B, the molarity of the sulfuric acid, now we just go through our titration calculation steps here. The titration calculation steps, we have the balanced reaction, that's good. Now we need to basically get to moles of the known side and then use that to get the moles of the unknown side. So in this case, if I look at the given information, I have 10 milliliters of sulfuric acid. I'll just arbitrarily use blue for the sulfuric acid. So 10 ml sample of sulfuric acid. Then it's titrated with 2.12 molar sodium hydroxide. That's the concentration of the base. The equivalence point is reached when 35.08 milliliters of NaOH have been added. So I can see that I have both the molarity and the volume of the NaOH, so that's my known side of my titration. So the known side is the NaOH, so that's where I want to start then. In general, if I want to write this as a normal stoichiometry calculation, I'm going to start with the quantity of the known. In this case, a quantity of NaOH. So that would be the milliliters then. So I would start with 35.08 milliliters of NaOH. Then milliliters needs to get converted to base SI units, so times 1 liter divided by 1,000 milliliters. Now I'm in liters of NaOH. Then to convert from liters to moles, I use the molarity as my conversion factor. So what 2.12 molarity means is 2.12 moles is equal to 1 liter for this substance. So times 2.12 moles for every 1 liter. I had liters on the top, so I need to put it on the bottom in my conversion factor. That now, if I'm keeping track of what cancels here, I've canceled milliliters, I've canceled liters, and I'm now in units of moles of NaOH. I'm comfortable stacking one more stoichiometry calculation onto there and going all the way to moles of unknown. So to get to moles of unknown, I just need to use the balanced equation. The reaction here I have is 2 NaOH, or 2 moles of NaOH is equal to 1 H2SO4, using the coefficients from the reaction. Since I have NaOH, that needs to go on the bottom, so times 1 H2SO4 over 2 NaOH gives me my final answer here. For this part, I'm not done yet. I haven't reached the molarity of the sulfuric acid, but I'll at least have moles of H2SO4, which is pretty close to where I need to be. So I get 0.03718 moles of H2SO4. Now the last step is just to use the moles of the unknown and the other given information to solve for what I need. So I now have moles of H2SO4. Originally I knew the milliliters. I'm trying to solve for molarity. So here I would just use, say, the definition of molarity. So I can use molarity is equal to moles over liters. And so the moles is the answer from part 2, 0.03718 moles. Then the liters of H2SO4 is 10 milliliters, which 10 milliliters, again, I can do a unit conversion times 1 liter over 1,000 milliliters, or just move the decimal place 3 places left. Either way, I should get 0.010 liters. So divide by 0.010 liters. In this case, when I do that, I should just get 3.718 molar. Technically, for sig figs, I'm only at 3 sig figs due to the molarity of the sodium hydroxide, so I should go to 3.72 molar as my final answer here. So here's our final summary slides from titrations. One thing we have is just sort of stoichiometry review. For the equivalence point calculations, write your balanced equation, find moles acid or base at the equivalence point, that's sort of the known side, then convert it to the moles desired or the unknown side using the balanced equation. I like to combine these two steps into one big stoichiometry calculation, but of course you could break it out separately. And then step 4 is just finding whatever the desired thing is. So using that moles from step 3, along with any of the other given information from the problem, you should be able to get to the final answer. Remember that you're not given the unit conversion for milliliters to liters. Just know that prefix as one of the things you're expected to know. 1 liter is equal to 1,000 milliliters. This summary slide tries to summarize all the information about the weak acid titrated with strong base curve, because that's the one where you have extra information. In this case, you start with the weak acid, enter the buffer region where the half equivalence point occurs. Equivalence point, halfway there is the half equivalence point, where you're at that best buffering point, and the pH of the solution is equal to the pKa of the weak acid. Then when you go to the equivalence point, that's where we can sort of distinguish a strong acid from a weak acid. So weak acid titrated with a strong base has a pH greater than 7 because of the production of that weak base in solution. Again, or think about it as the sort of strong base wins out over the weak acid and forces the pH basic at the equivalence point. Strong acid, strong base, you just have a neutral salt, so that's sort of that perfectly balanced titration where the pH is equal to 7 at the equivalence point. And then if you titrate a weak base with a strong acid, the strong acid wins out and you end up slightly acidic due to a weak acid in the solution at the equivalence point. Once you're past the equivalence point, of course, you just have excess base or acid, and there's no longer any difference between strong and weak acids. All in all, titrations really summarize a lot of our acid-base chemistry, can get a lot of information about different strong and weak acids and bases, and are used in many different applications of chemistry.